In this video, we're going to discuss simple harmonic motion. This topic can be a bit challenging, as you can see from the large number of equations shown, but we'll go over it carefully. I'm going to leave this screen up a little bit longer so you can go back and refer to it if you need to. Simple harmonic motion is a type of periodic motion or oscillation that can be described as a sinusoidal or cosine function of time. It also has a point of stable equilibrium that a restorative force tries to return the system to. Examples of simple harmonic motion are the spring mass, the simple pendulum, and the torsion or angular pendulum. We will discuss these later. The cosine equation that describes simple harmonic motion as a function of time is as follows. So x at times t is equal to xm, which is the amplitude, which sometimes in a formula is written as a, times the cosine of omega t, where omega is the angular frequency of the oscillation, t is time, and phi is the phase angle. Now this phase angle is what tells us what position t equals 0 is. And that's usually given in radians. So this equation, we'll call equation 1, oscillates and repeats itself every 2 pi radians, which is one cycle. So when omega t plus phi is equal to 2 pi, we get a repetition of the cycle. We can also define some terms. So frequency, given as f, is equal to the number of cycles per second of the oscillation. And the units for that is hertz, or Hz, where 1 hertz equals 1 cycle per second. The period, or t, is equal to the time it takes to do 1 cycle, and that's equal to 1 over the frequency. And the angular frequency, omega, is equal to 2 pi over t, which then is also equal to 2 pi f. And the units for period is second, and the units for omega is radians per second. I graphed out the equation x of t equals xm cosine omega t plus phi to show how the terms apply in the graph. So for the black line, we have phi is equal to 0, and the cosine peak starts at t equals 0, and you could see it has a period of t1. Now, if you go from phi equals 0 to phi equals a negative pi over 4, this shifts the graph to the right. So when phi is negative, you're actually shifting the graph to the right on this cosine curve. But you can see that the period is the same, t2 equals t1, and xm and minus xm, that's the amplitude, and that's the same. Now, for the blue graph, we're back to phi equals 0, so the peak starts at t equals 0, but in this case, the frequency is 2 times the frequency of t1 or t2. You have twice as many cycles in a unit of time. And this is how these factors affect the graph. Now let's look at velocity with simple harmonic motion. We know what our x value is, and the velocity in terms of time is simply dx of t times dt, which becomes a minus omega xm times sine omega t plus phi. Okay, because the derivative of a cosine is a minus sine, and we take the omega out as the constant in front of t. And this is called the velocity amplitude. So it's kind of similar to the xm in our position equation. Now, note with this velocity equation that if you have an oscillator that is oscillating about its equilibrium point, which is here, that the velocity is maximum at the equilibrium point, where x is 0. You get the maximum velocity, and it reduces as it goes to positive or negative xm. So the velocity at plus or minus xm is equal to 0, and that's where the oscillation reverses. And in addition, that's where the acceleration is the maximum at xm. Now let's look at acceleration. So acceleration is equal to dv of t dt, which comes out to be minus omega squared xm times cosine omega t plus phi, because the derivative of the sine is the cosine. And since, and this is called the acceleration amplitude. But notice that xm cosine omega t plus phi is simply x of t. So acceleration of t is minus omega squared times x of t. And we will see later that this is also equal to a minus k over m times x of t. I also want to point out that acceleration in simple harmonic motion is always opposite to the direction of displacement, hence the negative sign, and it's related to the position x, because omega squared is a constant. I had earlier mentioned different types of simple harmonic oscillators, so let's look at them. The first one we'll look at is a spring mass oscillator. And that's basically, you have a spring and a mass, and this mass is either pushed in or pulled out and let go, and the mass will bounce back and forth in a form of oscillation, and this is the x direction. So what can we determine about this system? Well, we know force equals ma from Newton's equations, which for a spring mass is equal to m times minus omega squared x. So basically, the force is minus m omega squared x. And this looks very similar to Hooke's law for a spring. If you remember, that's force equals minus kx. So if we call this k, k would be equal to m omega squared. In which case, we then can find that omega, the angular frequency, is equal to the square root of k over m, where k is the spring constant, which is equal to 2 pi over t, the period. And we can also say that the period is equal to 2 pi times the square root of mass over k. So what this tells us is that if you have a stiff spring where k is high, it has a large angular frequency. That means it'll move back and forth very quickly, and a small period. It does that in a short period of time. And if you have a large mass, we have a small angular frequency. It'll move slower, but the period will be larger. It'll take more time to do that. And note that the horizontal spring mass is basically similar to a vertical spring mass. The only difference is where you set your equilibrium point of x equals 0, because this will hang and gravity will pull this down, but otherwise the math is the same. So what about the energy in a spring mass oscillator? Well, we know that the only work being done is in the horizontal direction, so that will contain the energy. So our total energy is equal to kinetic plus potential, and that's equal to a constant. The energy can transform back and forth from kinetic to potential, but the energy stays constant. So let's look at this. Our potential energy is given as 1/2 kx squared, and if we use the equation for x, the cosine equation, that's equal to 1/2 k xm squared times the cosine squared of omega t plus phi. And kinetic energy is equal to 1/2 mv squared. And if we use the equation for velocity that we derived, that becomes 1/2 m omega squared xm squared times sine squared omega t plus phi. Now, we know that k is equal to m times omega squared, so the kinetic energy becomes 1/2 k xm squared sine squared omega t plus phi. Well, if we add 1 and 2 to give us our total energy, which is 1 plus 2, we get that becomes 1/2 k xm squared times cosine squared omega t plus phi plus sine squared omega t plus phi. And guess what? This turns out to be equal to 1. So our total energy becomes 1/2 k x m squared. And this is a constant. Now, you can also solve for v of x. instead of v of t. And that's equal to a plus or minus square root of k over m times xm squared minus x squared. And that gives you the velocity of the spring mass determined by x. And we can also solve for v max. That becomes the square root of k over m times xm. Let's look at another type of pendulum, a torsion or angular pendulum. And this is a system that has a thin wire, or sometimes even a thin rod, that is attached to some form of disc. Okay, this is a disc, this is a wire, and you have it move through an angle of theta, and it rotates back and forth. It's kind of like what happens in a watch. So what can we find out about this type of torsion pendulum? If it's rotating through an angle theta, then the torque that is rotating it is equal to minus capital kappa times theta, where this is defined as the torsion constant. So that's capital K, or kappa. Well, we can then find that the period is equal to 2 pi times square root of the inertia over K. And I is the rotational inertia of the disk. We can also then find that omega is equal to K over I, and frequency is equal to 1 over 2 pi times the square root of K over I. And these derivations are given in the textbooks, but we'll use these later in solving problems. And let's look at one more type of pendulum, and this is the simple pendulum. And this is where you have a mass or a bob, a weight, extended on a massless string that cannot stretch. And this would be vertical. And it moves an angle theta. And this again goes back and forth. Okay, and if we draw a free body diagram for the bob, okay, this string has length L, and that has a force equal to the torsion, and you have the weight of the mass, or the force due to gravity, and we have here Fg cosine theta, and in this case we have Fg sine theta. So in this case, there's a restorative force trying to move the bob back to the equilibrium point. And it's an equilibrium or restorative force, and that's tau is equal to minus L times Fg sine theta. That's just the force over the distance. So the distance is L, and the force is Fg sine theta. We also know torque is equal to inertia times angular acceleration, where I is the inertia of the pendulum, and the force of gravity is equal to mg. So if we put these together, we end up with minus L mg sine theta is equal to I times angular acceleration. Now, we're going to assume that theta is very small, because when we do that, then sine theta approximates theta. So if we do that, we then get L mg theta is equal to I alpha, or alpha is equal to minus mg L over inertia times theta. And we can also find that our angular frequency is equal to mgl over I, the square root, which becomes the square root of g over L. Our period becomes 2 pi times the square root of I over mgl, which becomes 2 pi times the square root of L over g. And our frequency f is equal to 1 over 2 pi times the square root of g over L, the inverse of period. So that was a simple pendulum, but that was just a bob on a string. Well, what if you had a more complicated distribution of mass? So for example, you have some type of structure just sitting here like this that's pivoting through this point, but its center of mass is down here, and this thing is swinging back and forth. This is no longer simple. Well, if we take this distance h between the point it's pivoting on and its center of mass, we can find that the period for a physical pendulum is equal to 2 pi times the square root of I over mgh. Omega is equal to the square root of mgh over I. And in this case, I obviously is more complicated. I also want to briefly mention uniform circular motion. And I do that because this can be described as a form of simple harmonic oscillation or simple harmonic motion. So if you have an object moving around in a circle, and if you view the motion from the side of it in the plane that it's moving, and you have an object here, you will see this object moving back and forth. And that is a form of simple harmonic motion. And that could be described by our equations, and you can plot that just like you would any oscillator. Now let's discuss damped simple harmonic motion. So with regular harmonic motion, we see that the motion pretty much stays continuous. But with damped harmonic motion, you'll get a motion that gets smaller and smaller and smaller until finally it peters out. And things like air or any type of fluid, water or oil, can dampen the oscillations. And this is due to an external force which converts the mechanical energy of the oscillator into thermal energy. So we'll call that external force that dampens an oscillator F sub D. And that's equal to minus B times velocity, where B is the damping constant. And its units are kilograms per second. And again, V is the velocity of the oscillator. So the damping force depends on velocity, because B is a constant. So let's look at this. If we have a force in a linear oscillator, like a spring mass system, we know that's equal to minus kx. Okay. Then from Newton's second law, we find that minus bv minus kx equals ma. And we're assuming that the force of gravity is negligible. So if we bring these two sides over, we get ma plus bv plus kx equals 0. And that means that m times second derivative of x with respect to time plus b times the first derivative of x versus time plus kx equals 0. Now this is a differential equation which you will learn to solve later on, but the solution actually turns out to be x of t is equal to x maximum times e to the minus bt over 2m times the cosine of omega prime t plus phi. And in this case, omega prime is equal to the frequency of the damped oscillator. And xm is the initial maximum amplitude before damping. And you can also solve for omega prime. That becomes the square root of k over m minus b squared over 4m squared. So this is the equations that are used with a damped simple harmonic oscillator. Now, if there's no damping, then the damping constant is equal to 0, and omega simply becomes the square root of k over m. And x of t simply becomes xm times the cosine of omega t plus phi. And these are what we had before when we had no damping. On the other hand, if b is very small, if there's just a little bit of damping, then the angular frequency of the damped oscillator approximates that of the undamped oscillator. And if b is very large, then the oscillation frequency will become 0. And in this case, b will be equal to 2 times the square root of km. Now, at this value, where your damping is very high, you get what's called critical damping. And that means that you basically have no oscillation and the system returns to its equilibrium point right away. So instead of this or this, you end up with this. So that's critical damping, where there's no oscillation and it just goes back to its equilibrium point. And with a damped oscillation, energy is not constant. It varies with time. So the energy with respect to time in a damped system is equal to 1/2 k x m squared times e to the minus b t over m. Okay, so this exponential component will cause the energy to decrease exponentially with time until there is no energy left. Now let's talk about forced or driven oscillations. So instead of dampening the system, you're adding force to the system. So an example would be if you're pushing someone on a swing, where you're adding the energy of your push to their motion. In this case, our equation can be written as x of t is equal to xm cosine w sub d times t plus phi. And w sub d is the angular frequency of the external driving force. Now, with forced or driven oscillations, we find that when omega sub d equals the natural frequency, we get the maximum volume amplitude and the maximum amplitude of displacement. And this is called resonance. So when you hit the natural frequency of an oscillator with an external force of that same frequency, you greatly increase the displacement, velocity, and amplitude of that system. And this is what has caused buildings and bridges to fall down, this resonance frequency. Let's do some problems in simple harmonic motion. But this first problem brings up a couple things I'd like to discuss a bit further. The first is the use of the sine versus the cosine equation for simple harmonic motion. So we've been using x equals xm cosine omega t plus phi. We can also use x equals xm sine omega t plus phi. Either equation works and gives you the same answer. The difference is that if we plot the cosine graph, we have this, whereas if we plot the sine graph, we have this. So that's the sine and that's the cosine. So at t equals 0, the cosine graph, the cosine becomes 1, so x is equal to xm, as you can see here. However, the sine graph, that sine function becomes 0 and x becomes 0, which you can see on the graph as well. So the difference is just this shift in the graph, but either one works and either one describes simple harmonic motion the same way. The second thing I wanted to mention is the phase angle. So in this problem, it's a sine equation, so we'll draw that. But it says that at t equals 0, the displacement is 4 centimeters. So here's xm, and let's say that's 4 centimeters. And they're calling that t equals 0. Well, that means that there's a phase shift here that has to be accounted for. And the phase angle, phi, will account for that. So when you have a problem where at t0, x does not equal xm, or 0, then you usually need to use a phase angle. Okay, so now let's get back to our problem. The motion of a simple harmonic oscillator is given by x equals 8 sine omega t plus phi. Its period is 24 seconds. At t equals 0, its displacement is 4 centimeters. What is its displacement at 6 seconds? So our equation for this is x equals 8 sine omega t plus phi. Well, we know that omega is equal to 2 pi over t, so we can plug this in and rewrite the equation as x equals 8 times sine 2 pi over t, the period, times t time, plus phi. And we're at t equals 0. We have x equals 4. So we plug that in and get 4 is equal to 8 times sine 0, because t is 0, plus phi, or 0.5 is equal to sine phi, or phi is equal to the arc sine of 0.5, or phi is equal to 30 degrees. So now that we know phi, we can use our sine equation to find our displacement at 6 seconds. So again, x equals 8 sine 2 pi over period times time plus phi, which is equal to 8 times sine 2 pi over 24 times given as 6 seconds plus 30 degrees, which is equal to 8 times sine pi over 2 plus 30 degrees. Well, that's in degrees, that's in radians, so we got to convert to one system of units. So we will use degrees. Pi over 2 is 90 degrees plus 30 degrees, or 8 sine 120 degrees, or x is equal to 8 times 0.87, or x is equal to 6.9 centimeters. Let's do another problem. A spring mass system is oscillating with an amplitude of 10 centimeters, a velocity of 2 meters per second, and acceleration of minus 20 meters per second squared at that position. What is its period? What is the phase angle? Well, we're given the velocity and acceleration. So let's write out our equations for those. Well, first we know that x is equal to x maximum, or amplitude, times cosine omega t plus phi. We know our velocity is equal to minus omega x maximum times sine omega t plus phi. and acceleration is equal to minus omega squared xm times cosine omega t plus phi. So first we want to find what its period is. So what we're going to do is divide acceleration by position. So if we do a over x, that's equal to minus w squared xm cosine omega t plus phi over xm cosine omega t plus phi, which is equal to minus omega squared. And we divided those two so we could find omega, and from that we can get the period. So we were given our acceleration as 20 meters per second minus 20, and our position as 10 centimeters, which is 0.1 meters. So omega squared becomes 200. Omega is equal to the square root of 200, or omega is equal to 14 radians per second. And we know that period is equal to 2 pi over omega. So that's equal to 2 pi over 14, which becomes 0.44 seconds. That's our period. Now, we want to know what is the phase angle. So for this one, we're going to divide velocity by acceleration, and we're going to use time equals 0. So that's equal to minus omega xm sine omega t plus phi over minus omega squared xm cosine omega t plus phi, which ends up being 1 over omega times tan omega t plus phi. And at t equals 0, this becomes 1 over omega times tan phi. And we know what our velocity and acceleration is. That's 12 over 20 is equal to 1 over, we found omega above, 14 times tan phi. So tan phi is equal to 12 over 20 times 14, which is equal to 8.48. So phi is equal to the arctan of 8.48, or phi is equal to 83 degrees. Our next problem reads, what is the maximum velocity of a spring mass system with a mass of 2 kilograms, a spring constant of 1 Newton per meter, and an amplitude of 0.4 meters? So we can use conservation of energy to find Vmax. So if we draw our graph, we know total energy is equal to potential plus kinetic, kinetic plus potential, and kinetic is maximum when x is 0, where it's going through equilibrium, and potential energy is maximum at our maximum amplitude. So if we go with potential energy, in this case, potential energy is equal to U equals 1/2 K x max squared, which in this case is equal to 1/2 K, which is given as 1, times x max squared, which is our amplitude of 0.4 squared. So that is equal to 0.08 joules. So that's our total energy when it's all potential. That's going to equal our total energy when it's all kinetic. So kinetic energy is given as 1/2 m v max squared. So that will now become equal to 0.08 joules. And if we solve for v max squared, that becomes 0.08 over 2 times the mass, which is given as 2, okay, which is 0.08. So that's Vmax squared. So Vmax is equal to the square root of 0.08, or Vmax is equal to 0.28 meters per second. Here's another problem. As a simple pendulum swings through a small angle, it hits an obstruction directly under its pivot point that only allows 1/4 of the string to continue its movement. What is the period of this system? So I tried to draw the system here. You can see a pendulum, and as it swings to the right, the string hits this obstruction, and only 1/4 of it continues. It then swings back to the original point to give one cycle. So our period is made up of half the period of the long string plus half the period of the 1/4 string. And we know that for a pendulum, t is equal to 2 pi times the square root of L over G. So we want to find this time here. So that's equal to 1/2 times the period of the full string, which is 2 pi times the square root of L over G, plus 1/2 the period of the quarter string, which is 2 pi plus the square root of, well, L is L over 4 now, over G, which actually becomes 1/2 2 pi the square root of L over G plus square root of 1 over 4 is 1 over 2, so that becomes 1/4 times 2 pi square root of L over G. These are the same, and that's equal to the period of the full string. So the time it takes is actually equal to 3/4 times t, which is what the full string would have been, 2 pi times the square root of L over G. So that's what the time of the period of this new system is. Here's another problem. A disk pivots at its edge. What is its period? What will be the length of an equivalent simple pendulum? So we have a disk, and it's pivoting on its edge, going back and forth. So we know that for a physical pendulum, the period is equal to 2 pi times the square root of moment of inertia over mgh, where h is the distance from the axis of rotation to the center of mass. So in this situation, h is equal to r, because that's the center of mass and that's the radius. Now the other thing we need to determine is what the moment of inertia is. Well, if you remember the parallel axis theorem, that says that the moment of inertia of an object is equal to the moment of inertia through its center of mass plus mr squared, where r is the distance from the axis of rotation to the center of mass. So for a disk, in this situation, it's x equal to 1/2 mr squared plus mr squared, which is equal to 3/2 mr squared. So now we can plug that into our equation for a period. Period is equal to 2 pi times the square root of I, which is 3/2 mr squared, over mgr. So that cancels out. One of these cancels out. That becomes 2 pi times the square root of 3r over 2g. And that's what the period would be for the disk rotating at its edge. And now we're asked what would be the period of an equivalent simple pendulum. And if you recall, a simple pendulum is a weightless string with a mass at the end. So the equation for the period of a simple pendulum is equal to 2 pi square root of L over G. And we want to know what L would be when it's the equivalent to this period. So that's equal to 2 pi the square root of 3r over 2g. So those cancel out. We get L over G is equal to 3r over 2g. These cancel out, and we get L is equal to 3/2 r. So that would be the length of a simple pendulum that would be equivalent to the disk in the system. Our next problem is a metal hoop is suspended by a peg. It can oscillate side to side in its plane with period T1. It can also oscillate back and forth perpendicular to its plane with period T2. What is the ratio of T1 to T2? So let's try to draw this. So we have a metal hoop, and it's got a radius r, and for T1 it's rotating side to side. And now we take the same hoop, radius r, and in this case it's rotating back and forth. So for a physical pendulum, we know that T period is equal to 2 pi over the square root of I divided by mgh. In this case, h is equal to r again. And using the parallel axis theorem, we find that the moment of inertia for the first disk is equal to mr squared plus mr squared. And the moment of inertia for the second disk is equal to 1/2 mr squared plus mr squared. So this one is 2 mr squared, and this one is 3/2 mr squared. So now we know that from our equation for period, T1 is equal to 2 pi times the square root of 2 mr squared over mgr, which is equal to 2 pi times the square root of 2r over g, and T2 is equal to 2 pi times the square root of 3/2 mr squared over mgr, which is equal to 2 pi times the square root of 3r over 2g. And we wanted to know what the ratio of T1 to T2 is. So that's equal to 2 pi times the square root of 2r over g divided by 2 pi times the square root of 3r over 2g. Those cancel out, the g's cancel out, the r's cancel out, so that's equal to the square root of 2 times 2 over 3, which is equal to the square root of 4 over 3. So the ratio of T1 to T2 is equal to 1.2. Here's our last problem. A motor of 2,000 kilograms sits on a recoil spring that damps the recoil to the point that there is no oscillations. This is critical damping. The recoil spring recoils 1 meter with an initial speed of 10 meters per second. What is the spring damping constant B? We know for critical damping, the damping constant B is equal to 2 times the square root of the spring constant K times mass M. So we could find K using conservation of energy. So we know that 1/2 m V max squared is equal to 1/2 K x sub m squared. That's the maximum kinetic energy equals the maximum potential energy. So putting those numbers in, 1/2 times 2,000 times V max, in this case is 10 squared, is equal to 1/2 K times x sub m, which is 1 meter squared. Those cancel out. You get 2 times 10 to the 5th is equal to K. So knowing that, we can find B. B is equal to 2 times the square root of K m. So that's equal to 2 times the square root of 2 times 10 to the 5th times the mass is 2 times 10 to the 3rd. Is equal to 2 times the square root of 4 times 10 to the 8th. That's a 5, which is equal to 4 times 10 to the 4th Newton second meter, or B is equal to 40 kilonewton second meter.